So here is our parallelogram. We got V here, we got W here, we form the parallelogram as before, and we got the altitude, same altitude. We know that altitude has this magnitude, but we're not going to use that. Okay, what we're going to do is we're going to calculate this based on the cross product. Okay? Well, the altitude, and we're not going to talk about the cross product just yet, but the altitude is the magnitude of V multiplied by the sine of theta. How do I say that? Well, right here is a side of length magnitude of V. Right here is a right triangle where magnitude of V is the hypotenuse. Theta is down here opposite this side, so that this side must be magnitude of V times the sine of theta. Just very straightforward triangle trigonometry. Okay? So that the area is what? Well, it's the magnitude of W, which is the base, times the magnitude of V times sine theta. In other words, magnitude of the base times the altitude. That is equal to the magnitude of the cross product. Just as the magnitude, well, the dot product is equal to magnitude of V times magnitude of W times the cosine of theta. The magnitude of the cross product is magnitude of V times magnitude of W times the sine of theta. Okay, so that the V cross W gives us the area of the parallelogram. Now, I didn't go into detail, and I'm not going to do it just yet, but I might do it a little bit later, but I really kind of expect you to be able to read this. Let's go to 3 dimensions where we've got V, W, and U. Okay, well, let's say that V and W can be used to form a parallelogram down here. We can find the area of that parallelogram. It's just V cross W, magnitude of V cross W. Okay? Then and I kind of left something out here. I'll put it in right here. It should just be the absolute value of this, because this could come out negative. Okay, but let's develop it. Okay, so the area of the base is the magnitude of V cross W. Okay? Then this three-dimensional figure, this parallelepiped, one of my favorite words, has an altitude which is could be obtained by projecting U down to the plane formed by V and W, because the altitude of this figure is just the distance between this plane and this plane. Okay, and that is equivalent to projecting the U vector down here. Now, I'm not going to write out all the details, so I'm not even going to talk the details, because that might be confusing. If you take the vector U and dot it with the vector V cross W, you get, well, the projection of the U vector onto the V dot cross W is here. Okay, and that's the altitude. That's equivalent to this altitude. That's exactly the same vector as you get if you project U down into this plane. Again, your book gives you that in more detail, and I might well go over it in more detail with a bigger picture and more explanation. If you work out the expression for the volume of this thing in terms of this projection of the U vector onto the V cross W vector, and simplify it, you find that the volume is just U dot V cross W, or at least the magnitude of U dot V cross W, because of course U isn't necessarily in the direction of V cross W, or it doesn't come out of the plane in the same direction. If W was here and V was here, then, and actually I kind of wrote that wrong. V cross W, if V is here and W is here, would be down this way. In any case, the volume is this, and since I kind of drew that arrow in the wrong direction, I can fix that real easily. Now this vector is W, this vector is V, so the V cross W is in this direction. Okay. So you can think through exactly how that works out. Again, I don't have room to write out everything I need to. But the projection of the U vector on V cross W is the altitude, and if you multiply that then by the magnitude of V cross W, you get the volume. And that's exactly the way it works out if you do this dot product of U with the V cross W. We call this the triple the triple product, okay? It's a combination of dot and cross product. And that's a very, very handy thing to know.